Hello there, Mr. Sutton here with the AB Calculus 412 Extra Practice number 5 solutions on motion. For this set of problems, we have a ball being tossed from the top of a tower, and the function that describes the height above the ground for the ball, t seconds after tossing, is this S formula right here. So based on that, we have a number of tasks, the first of which is to find the instantaneous velocity at 1 second. So for that, we need a velocity, which is really S prime of t. So we need S prime of 1 in this case if we want velocity at 1 second. And this is a calculator question, so since you already have the original function, you can actually just take the derivative of that directly on the calculator without showing what the derivative looks like algebraically. So here I am on the calculator. I've entered my S function in the y equals under y1 right here. And now let me just quit out of there and use the derivative function. That's going to be math 8. And I'll do dx. I'll do alpha trace y1 because that's where I stored my S function that I'm taking the derivative of. And I want to evaluate this at x equals 1, or t equals 1 in this case. Comes out to 32. And since this is velocity, and we have distance units of feet and time units of seconds, this would be in feet per second. On this problem, we want to find the height of the ball after 4 seconds. So we've already got a function for height. That's the S function here. So we just need to find S of 4, and let's do that on the calculator. Since I already have the S function stored as my y1 on the calculator, I'm just going to do alpha trace, select y1, open a parentheses, and plug in 4. And that's going to give me 86, and that's going to be in units of feet. For this problem part, we want the velocity of the ball after 4 seconds. So this is another one where we have to plug 4 into something into the v function. But again, because we're just plugging a single number into it, I'm just going to take the derivative of the distance function here and plug 4 into that on the calculator. So v of 4 is really just, again, S prime of 4. Let me do that on the calculator now. So on the calculator, if you do math 8, that brings up this derivative function. And in this one, I entered x for the dx here. We have y1. I did alpha trace y1 to get that. And then we're just doing this at x equals 4 for a grand total of negative 64. Since it's velocity, this is going to be feet per second. On this part of the problem, they want the initial velocity at which the ball was tossed. So for this, we need to find the derivative of the motion function here at 0. So we're going to do S prime of 0 on the calculator. So here we are back on the calculator. We've already done S prime of a few numbers by now. We're just going to use 0 instead of those other numbers, but otherwise the setup is exactly the same for problems as problems parts A and the last one, part C. So here we go. Initial velocity is 64, and that is in feet per second. For this one, we want to find the max height reached by this ball. So for that, I am going to finally define the velocity function. That's again going to be S prime of t, which is going to be negative 32t, so just using the power rule here, plus 64, and that 86 is gone because it's a constant. And now to find max height, I need to know when velocity changes direction, specifically when it changes from positive to negative. So I'm going to go ahead and set this equal to 0 and find critical values. Now, I could find this on a calculator. The reason I'm going to do it algebraically is with a calculator, you're never really sure if you found all the critical values. I'm just going to go ahead and set this equal to 0 and solve algebraically, because algebraically, I know what all the different answers are going to be. So if I subtract 64, divide by negative 32, that's going to be 2, time equals 2. This is our only critical value. So let me go ahead and test that on a number line. So this is a V line here. We've got 2 for my one critical value. And doing a little sign analysis, plugging in something less than 2, let's do 1. This would be negative 32 plus 64, which comes out positive. And if I plug in a number bigger than 2, like 3, well, now we've got negative 96 plus 64, comes out negative. Since V changes from positive to negative at time 2, that means that S has a local max at time 2, and since t equals 2 is the only critical value, that means that S has an absolute max at time 2. So we've established that 2 seconds is the time of our highest height. So we just have to plug that in to the s function now in order to actually find that height. And for that, I will use the calculator. So here we are, just plugging 2 into my y1 where I stored the s function. And this comes out to 150, and that's height, so feet. For this problem part, they want to know when the ball will hit the ground. So I'm going to use the s function here because that talks about how high above the ground I am. I want to find out the t value when s takes on a value of 0, because that's when you're at the ground, when your height above the ground is 0. So we're going to solve s of t equals 0 on the calculator. So recall that I stored my s function as y1. I'm just going to graph it now and see where it touches the x-axis. And for my window, I'm going to use a window, well, we don't need negative time, so I'm going to use a window from 0 to 10. And let me just do a zoom 0, and see what happens. So there is my distance function, my height function, and we're crossing, this looks to be roughly 5, but let's do second trace and zeros just to make sure that's actually 5. So enter a little bit to the left, press enter again a little to the right, press enter one more time, and that is not exactly 5. It's about 5.0619. Now I'm going to go ahead and store this as a variable on my calculator and on paper. So let me just write down what I've got on the paper here. So there was my graph, which I'm just showing you for reference here. We said time 5.062 seconds was when we hit the ground, and I'm going to store that as A on my calculator because I have a feeling I'm going to need that time again. And if you read ahead on part G of this problem, you do end up needing to know what that time was. So let me quit out of my graph, and let me just press stow for store, and let me just do alpha A. So now I can bring back that time whenever I need to. For this problem, I want to know the velocity of the ball the instant it hits the ground. So recall on part F that I figured out what time the ball actually hits the ground, and I stored that as A on my calculator, and I also labeled it as A in my work. So I can plug A into some function. Now, which function am I plugging it into? Well, I could go with s prime, because that is the same as velocity, or I could actually just plug it directly into v, because I've actually defined v of t at this point algebraically back in problem part E. So either way, let's plug it in the calculator. So back on my calculator, I hadn't done this yet, but I entered my actual velocity function, negative 32t plus 64, in as y2. So now if I just quit out of there, I can do alpha trace, and then I select y2 now, where I stored my velocity function. And I'm going to open that parentheses and plug in alpha a, where I stored the time that the ball hits the ground. And then press equals. We got negative 97.980 if we round it off to 3 decimals. And that's going to be in feet per second because this is velocity. For this collection of problems, we have a snowball being thrown in the air, and the height is given by this s of t function. First task is to find the velocity and acceleration functions. So velocity, which I'll call v of t, that is going to be the derivative of height in this case, or s prime of t, which is going to be negative 32t plus 96. And then for acceleration, that's going to be the derivative of velocity, or the second derivative of s, either way, and that's going to be negative 32. For this part, we want to know when the snowball hits the ground, so I need to know when s of t, which equals all this stuff, takes on a value of 0. And this is a no calculator problem, so I'm going to have to do this algebraically. I can start by factoring out a negative 16, and you might have to factor out a few things before you realize that you can take out 16, but you can. So if I take 16 out, that's going to leave me with t squared, and this is going to be minus 6, and then this is going to be minus 7 over here. So we can factor a little further, things that multiply to negative 7 and add up to negative 6. We can write t plus 1 and t minus 7. So we see that my critical values, my places where the snowball hits the ground anyway, I don't know if I want to call them critical values, but at least what zeroes out this equation is going to be t equals negative 1 and t equals 7. Of course, negative time doesn't really make sense in this context. I can't hit the ground before I throw the snowball. So we're just going to go with 7 seconds for our final answer. To find the maximum height of the snowball, I need to find critical values, and for that I need my velocity function again. So here is my velocity function from part A, and I'm just going to set that equal to 0 and find critical values. So let's see, if I subtract 96, divide by negative 32, we see that our only critical value is at t equals 3 seconds. So let me put that on a number line, a v line, and test some values around that to do a little sign analysis. So if I plug in a number less than 3, like 2 or 1, either of those, I get, let's see, this will be negative 32 plus 96. That's going to be positive. And something bigger than 3, let's go with 4. That'll be, well, whatever it is, it's more negative than 96 is positive. So that's also going to be a negative. We see that v changes sign at time 3. Changes from positive to negative specifically at time 3. That implies that s of t has a local max at time 3, and now since 3 is the only critical value for velocity, that implies that it is also the absolute max for the s function. Which means to find the absolute height, max height, I just have to plug 3 into the s function itself. So let me go ahead and do that. That's going to be negative 16 times 3 squared plus 96 times 3 plus 112. And let's just go through this and do the arithmetic. This is numerically equivalent to whatever the answer is, so you don't have to simplify. You could just stick units on the end of this and call it a day. But if you want to simplify, this is negative 16 times 9. Well, let's see here. 9 times 1 is 90. 9 times 6 is 54. Add those together. This is negative 144. Over here, 96 times 3. 3 times 90 is 270. 3 times 6 is 18. 270 plus 18 gives us 288. And then we have a 112 that we're adding on the end there. Now this 112 seems kind of inconvenient, but it's actually really nice because 288 plus 112 comes out to exactly 400. So you're basically just doing 400 minus 144, which is going to be 256, and that is the height, so that's going to be in feet. For this part of our problem, we want to know at what speed does this snowball hit the ground. So recall from part B that we found the time the snowball hits the ground. That was 7 seconds. So we basically need to plug 7 into something to give us the speed. Now speed is the absolute value of velocity. So if we find the velocity at time 7, we just need the absolute value of that to get the speed. So velocity, again, that's going to be negative 32 plus 96. So this is going to be negative 32 times 7 plus 96, which is going to come out to, well, let's see here. This is going to be 30 times 7 would be 210, plus another 14 for the 7 times the 2. So this is negative 224 plus 96. So that's going to come out to about negative 128. And then again, speed is just absolute value of velocity at time 7 in this case. So our speed is going to be 128, and our unit, since it's a rate of change of distance, this is going to be, let's see here, height of a snowball is given by feet. Okay, so we're going to have feet per second. On this problem part, we want to know after how many seconds is the velocity of the ball 32 feet per second. So we use our velocity formula, negative 32t plus 96 that we found a while back. Just set that equal to 32 and solve for t. So subtracting 96, that's going to be negative 64. Divide by negative 32, we have time equals 2 seconds. For this part of the problem, we want to know after how many seconds is the velocity negative 32 feet per second. So this is more or less the same setup as we did in part E of this problem, only now we're going to set our velocity function equal to negative 32 instead of positive 32. Still the same velocity function though. So if we subtract 96, that's going to be negative 128, and then dividing that by negative 32 comes out to 4 seconds. For this problem setup, we have a particle traveling on a straight line, and its position is given by this s of t function, which is in meters. Time is in seconds. We want to find the velocity and acceleration functions for this first part of the problem. For velocity, we need the derivative of position, s prime. That's going to end up being 3t squared, so just using the power rule here. And we have minus 8t plus 4t, and then that 5 is just going to become a 0. So that's velocity. For acceleration, we need the derivative of velocity or the second derivative of position, either way. So that ends up being 6t minus 8. On this part, we want to know when the particle changes directions. So basically, I'm asking at what t value do I have a sign change in the velocity function. So let me take my velocity function that I found in part A and just set it equal to 0 to look for critical values, places where velocity could change sign. And if I factor this now, well, this would split up into, let's see here, we've got a 3t and a t, and there's only so many ways to get 4. Let me guess negative 2 times negative 2. I'm guessing two negatives because it multiplies to a positive and adds up to a negative. So let me try this and see if it works. So 3t times negative 2 would give me negative 6t. Negative 2 times t would give me negative 2t. Negative 6t plus negative 2t does give me negative 8t. Yep, so this works. Awesome. Hey, how about that? I got it on the first try. So this equation is going to hold true. Our critical values are going to occur at t equals, let's see, if we add 2 and divide by 3, that's 2/3, and also t equals 2. So that's 2 potential direction changes, but we can't assume we're changing direction. We have to actually do a little sign analysis to make sure velocity changes signs at these critical values. So here is my v line, and I'm not worried about anything before 0, so let me just make that an endpoint. So there's 0, there's my critical value of 2/3, and also 2. I'm going to test out an x value in each of these intervals. So something between 0 and 2/3. How about 0? No, I can't use 0. How about 1/3? Yeah, let's go with that. I mean, algebraically, 0 and 1/3 will have the same effect here, but it just looks cleaner if I'm not testing something that's realistically out of bounds. So testing 1/3, 3 times a third is going to be just 1. 1 minus 2 is a negative. 1/3 minus this 2 over here is a negative, so 2 negatives gives me a positive. And now something between 2/3 and 2, 1's a pretty easy number, so that's going to give me a positive times a negative, which comes out negative. And then between 2 and infinity, well, how about 3? So that's positive, positive, comes out positive. So I notice that I have sign changes in my velocity at 2/3 and 2. Because velocity changes sign at those two values, the particle is changing directions at those 2 points in time. On this problem, I want the velocity of my particle at 4 seconds. So recall from part A, we already wrote out the velocity function right here. Here it is again. So just doing v of 4, I'm just going to be plugging 4 in for all those t values. So that's going to be, let's see here, this is 3 times 16, which is going to be 48. Minus 32 is going to be 16. Plus 4 is going to be 20. So this is going to be 20, and that's going to be meters per second. On this problem, we want the acceleration of this particle at 4 seconds. Recall from part A, our acceleration formula was 6t minus 8. So this is going to be 6 times 4 minus 8, or 24 minus 8, which comes out to 16, and that's going to be in meters per second, or meters per second squared.